So welcome everyone. My name is Andrzej Czarny, and today I would like to talk about Java memory model. So we are mostly familiar with synchronized keyword and how immutable exclusion works, but we often forget that we also have to care about data visibility. A few words about me. I'm a senior software engineer. I work for Kara Technology in simulation algorithm development team. And we are one of the teams responsible for our new control system for our new warehouses, where we have thousands of bots which are picking grocery orders. So as you can understand, concurrency is quite important to us. So what we are going to talk today about, we will start with out-of-order execution. We will try to understand why multiple threads doesn't have the same point of view on memory. Then we will have a short introduction to JCStress framework, which is one of the frameworks from OpenJDK, which allows you to test assumptions from Java memory model. Then we will have some basic for JMM. We will try to understand some concepts and definitions. Finally, we will go to some examples and puzzles trying to test our knowledge. And we will have one slide about Java enhancement proposal 188, and some modifications which are required for Java memory model. All right, let's start with out-of-order execution. So there are two reasons. Well, in general, it's one reason. It's optimization, why we have something which is out-of-order execution. So we have something like compiler optimizations and then hardware and CPU cache optimizations. Let's start with compiler optimizations. So we know when we have our Java code, it will be compiled to bytecode using Java-C. Then it will be executed on JVM. And as soon as the JVM detects that specific method is executed a specific number of times, it will start optimizing, right? We have two compilers, C1 and C2. One is server, one is client side. But in general, Java 1.8, the JVM will detect which compiler to use when. And it will try to optimize our code. What kind of optimizations we can have? Well, if you have, of course, the first one is inlining. So instead of executing specific method, calling the method, the content of the method is copied to the specific place if it's short enough, which will reduce number of jumps which are required. If you have, for example, a short loop, so instead of creating the loop, the content of the for loop is just copied multiple times. If you have a method which is synchronized and you will call it from a loop, then compiler can detect that and put the synchronize around the loop, because entering and exiting synchronized block is expensive, and that will also optimize it. If you synchronize on something which is not visible for other threads, then compiler can detect that and completely remove the synchronization. And there's much more of them. Let's try to have a typical textbook example of this kind of optimization. So in this class, we have one flag, which is static flag, and it's properly not synchronized. And then we have our main method, which will create two threads. One thread is just going into the loop every time it iterates, it's trying to read the flag, and the purpose of the second thread is just to terminate the first one. We are waiting 1 second to allow the compiler to optimize, to warm up the JVM, and let's try to guess what will happen here. So we will have, of course, inlining, because get flag, you don't have to call it and multiple times, right? You can just get it once, and then iterate in the loop. The if statement will be executed only once, so after 1 second, it doesn't matter, so we can just remove that completely. And on the end, we'll have something like that, which means that there is no way that the second thread can terminate our loop, right? How do we know that? Well, you can provide extra arguments to JVM. It will provide you with the assembler version of this optimization. Then you can use JIT-watch, and you will have like nice tree view of your Java code, your bytecode, and assembler. And let's say that's my interpretation of the assembler outcome. And I think that's time for demo 1. So once again, this is our class. and we can just execute it. And the main point is that our flag is just static flag, right? We are not informing the compiler that we will use it from multiple threads. As you can see, I can run it as many times as I want. It doesn't matter. It will never finish. The nice thing about inlining is that you can disable it. So we can do something like can run our code a little bit differently. So we can provide -xx :inline, which will disable the specific optimization. And now compiler cannot replace our get flag, it will have to read it. So yeah, program has terminated. So yeah, we fixed our problem. However, we have disabled one of the most important optimizations on compiler, so it means that everything is slow now. So probably there must be a better way to do that. All right. So we know that compiler can reorder our code. How about our hardware? So most of us has quite high-level view on modern hardware architecture, which means, all right, I have a processor. It has some cores. I will have 2 threads which are running on core 0 and core 5. There is memory. What kind of reordering can we have, right? Thread 1 will access the memory directly. Then thread 2 will also access that memory. So when thread 1 is writing something, thread 2 can just read the value. Everything is fine. But in reality, it's not simple. The problem here is that accessing memory is quite expensive. So if you think about modern CPUs, single execution, single operation can be executed below 1 nanosecond. Accessing memory, well, that's like 60 nanoseconds, up to 100 nanoseconds, depending, of course, on your architecture and specifics of your hardware. But it's still a number of times more than single operation. So what will happen physically? How can we optimize that? Of course, we have to introduce number of caches, right? We will have L3 cache, which is a big one, is shared between all the cores. And then we'll have L2 and L1 caches, which are smaller and faster, which like access time around 1 nanosecond, for example, for one cache. But also, we will have something which is called store and load buffers. And I should probably explain what store and loads are. So store is quite simple because it's like writing to memory. So x equals 168, that's store, because we are storing 168 somewhere in memory. And load is just getting the value from memory. So if you get the y and you want to multiply by something, that's load. Why do we need store and load buffers? Well, our execution engine is like multi-pipeline thing. And in general, it will execute multiple micro-operations at the same time. So it can execute load and store almost in the same time. However, stores are more expensive to trigger, to finish that, because you have to share then the results of the store between other cores. So there is something like coherence protocol, which will try to exchange that information. So if we try to execute our code, we'll end up with something like this. So it will partially start executing the store. It will put in the store buffer. And as you mentioned, as you've seen on previous picture, we are quite lucky enough that value for y is already in our L1 cache, so we will not have a cache miss. So we don't have to refer to memory or directly to memory or to one L2 or L3 cache. So we can just simply get load first, and store is still not visible to other threads. So from perspective of C5, we've executed loads, and then finally we will execute store because store will be committed to the memory. Coherence protocol will try to exchange that information between caches, and in the meantime, it will also populate that into main memory. So that's our reordering. And as you can guess, that's not only possible reordering there. So we can reorder loads with loads, loads with stores, stores with stores. And this is even not complete table. And based on those reordering, you can distinguish between 2 different memory models for hardware. One is a strong memory model, so if it's like x86 architecture, which I currently have here, you can only reorder store with loads. If you are less lucky, for example, ARM v7 or any ARM or alpha, number of different reorderings are possible, right? Inside that table, you can also see some assembler instructions. Sorry for that. But they are quite interesting because those are stored memory barriers or memory fences. So if you think about volatile in Java, somewhere on the end, it will be replaced like on x86 architecture with mfence or locked, and it will prevent reordering on our caches, right? So if you look at that picture again, so if you have a volatile, it will just tell you that please commit the store buffer, the operation from the store buffer, which our volatile refers to, before you execute any further loads, and the reordering then is not possible anymore. All right, and now I think it's a good time to introduce JCStress framework. So there are two popular frameworks from OpenJDK which I use. One is JMH. So if you have to create a benchmark, always use JMH because it will properly warm up your JVM, give you nice statistics. It will save a lot of time. If you want to experiment with Java memory model and try to understand how it works, you can use JCStress. It's still experimental phase, however, it's already used on OpenJDK. There are hundreds of tests. I would suggest everyone to go there, check the test, and try to understand them because you can learn a lot. And also new features on Java, they are already covered if they are related to memory model with that framework. And if you want to create your own tests, that's quite simple. The framework is just annotation-based, so you have to provide add JCStress test annotation on top of your class, then add state, because it will contain some state, and you also can create add outcome, and that's our assertion. So in that case, we are assuming that we will get 1, and then it's expected, it's acceptable, interesting. It can be forbidden or just acceptable, and you can add some description. Inside the test class, you can include multiple methods, and you can have a number of annotations on those methods. So if you put an actor on a method, it's an entry point for the thread, and you can have multiple actors. So it means that multiple threads will execute those methods in the same time. If you add arbiter, you can have only one arbiter method, and that method will be executed after all threads has finished. So you can collect some results. You can also collect the results from your actors by passing a class, which is annotated with @results, and in that case, it's just II results. There are already a number of classes defined, and in that case, it's like 2 integer results. And the results are usually like strings, integers, longs. And there is also another mode for execution, which is mode termination, and this mode is more appropriate for our first example, where we had our loop, and then second thread is trying to terminate that loop, but you don't know if your thing will be successful, right, your termination. So in the meantime, framework has to detect that, all right, we've already sent some signals, so that's why we have a signal, but our thread is still running, so it has to terminate everything, because if not, then the program will run forever. All right, let's start with our first test. The only reordering which is possible from hardware on that architecture, of course, the test should be created in assembler if you want to really test it, but we will see similar reordering from our Java application. So let's think what we have here. So we have 2 threads, 2 actors, and our class will have X and Y. Of course, it's intentionally not synchronized, not properly synchronized, so we are creating a data race here. And the first actor is trying to write to X and read the Y. And the second actor is trying to write to Y and read the X. What kind of results can we get? Well, if first actor is executed as the first one, Y is still 0. So we have 0 in R1, and actor 2 will be executed. So X is already populated, so we have 0, 1. If we execute actor 2 as the first one, then we will have 1, 0. If we are lucky enough and both actors are executed in the same time, then we can get 1, 1, right? What's not possible here is to get 0, 0. So if you have 0, 0, it means that something has to be reordered, because every time when you execute one of those threads, we've already populated X or Y. Let's try to run that. All right, I should have here somewhere. Store load. So as you can see here, the outcomes, you can provide a number of outcomes. So 1, 1, 0, 1, and 1, 0 acceptable. 0, 0 is acceptable, interesting, because it's the only reordering possible on x86 architecture. And we can run our test. Oh, I should probably mention earlier how framework works. So it will instantiate your class, and as many times as it can for 1 second, create all those threads, get the results, and it will do it 4 times, and then provide you a nice summary of all the possible outcomes. It will also try to detect what kind of JVM you have, what kind of extra parameters you can provide to get the test more interesting, how many cores you have. Let me show you how it works. OK, so I have 4 cores, and from time to time you have to recompile. In general, you should create your jar and then run it from command line, and then everything is fine. If you run it from IntelliJ, sometimes it just doesn't like it. All right, one more time. Yeah, we have some results. And as you can see here, 0, 0, we have quite a lot of 0, 0s still. So this reordering is quite possible. How do we know that it's hardware, not compiler? Because in general, it could be also compiler. Well, we could disable compilation, but we can do something more interesting, because store load reordering is only possible when we have 2 cores. If you have single core, then there is something which is called store buffer forwarding, which means that the second thread, if it's executed on the same core, can just access the store buffer instead of going to L1 cache or another cache or to memory. So we can force everything to execute on single core, and we shouldn't have any 0, 0s. How can we do it? Well, of course, there's something which is called affinity. And on Windows, you have to go to your task manager and then find your IntelliJ. Yeah, it's here. So if you set affinity on your top process, then any other sub-process will inherit that affinity. So we can force now to run only on CPU2, for example. I should mention those are hyper-threaded cores, but it doesn't matter. All right, so everything will be slow now, but let's try it again. And so we have only 1 thread available, and no 0, 0s. We also don't have 1, 1, but if you think about 1, 1, it means that both threads has to be executed in the same time, and the content of the thread is quite small, so to hit the switching context in the middle is like quite unlikely, but we can force that if we want to. So we can do something like, if we are here, for example, we can do something like threads And that means that I don't want to execute anymore. Put me into my scheduler queue and let scheduler decide what to do next. And if we run it again, unfortunately slow because it's just one core. And now we have 1.1. But 0.0 is still not visible. What's also interesting here, which I should mention, is that this is like statistical base, which means that if you don't see the result, it doesn't mean that it doesn't exist. Maybe you haven't run it for long enough. Maybe you haven't run it on specific architecture. But if you see it, then it's certainly wrong. All right, let me remove the affinity, because for other tests, it would be horrible to run it with just single core. And set it to all. OK. So that was demo 2. And now, so we already know that number of reorderings are possible. We can try to run everything on single CPU or disable some optimizations, but of course there's a better way to do it, right? So we need a contract, we need some kind of contract between developer, JVM, and hardware. And this contract is Java memory model. So it will tell you how or when specific writes from one thread should be accessible to the second thread. And we are quite lucky enough in Java world that we have the first memory model in modern programming language. As you can guess, the problem is quite complex. So the first memory model was a little bit broken. Anyone is using Java 1.4? All right, that's good. So before Java 1.5 and before JSR 133, it was quite difficult to run something multi-threading in Java 1.4 because you couldn't have Threadsafe immutable objects. And what I'm referring to those is an immutable object where you can just share the reference to that object without any extra synchronization. So if I create a string, I can just pass the string to other threads. Everything's fine. So in Java 1.4, when you create a string in one thread, then in the same thread, you will create a substring and share that substring without extra synchronization. Other threads can see the substring, or if you're unlucky, they will see the entire string because the backing up char array is still there, and all you're just changing offset. And if offset is not updated, then unfortunately you have full string again. And also reordering between volatile and non-volatile fields were possible, which means that it's quite difficult to reason about what's really happening there. But now everything is fixed with Java JSR 133, Threadsafe immutable objects, more powerful volatile. All right, so what is it all about? What is the reason why we have Java memory model? So the base concept is that we want to create some kind of order of execution of our code. How can we do it? Well, Java memory model will introduce a number of actions, which are like writing to volatile, reading volatile field, start of your thread, or the first action in the thread. And the base idea is that they will combine two actions in something which is called synchronized with relations. And if we have those relations, then we can reason something about execution. So once again, those four are probably the most important one, a bit more than just four, but let's focus on those. When we unlock action on monitor, which means that we are exiting our synchronized block, and then other thread is locking, so entering our synchronized block, we have this nice synchronized with relation, writing to volatile and reading the volatile. Of course, the same volatile, the same field, right, and the same monitor. And then first action in the threads, the action that started the thread and first action in the thread will also have the synchronized with relation. And also final action in the thread will have synchronized with relations with a thread that detects that the first thread has terminated, for example, thread join. Why do we need them? Well, as I mentioned, we want to order something, right? So we need happens before order. That's the most famous order. And for single thread execution, if you have just thread A, it's quite easy to reason about, because if operation 1 comes before operation 2, then operation 1 happens before operation 2. It's like single-thread execution. For multi-thread execution, we have to search for our synchronized with relations. So if we look at those operations are less important. We have write to volatile and read to volatile, right? That's our synchronized with relation. Write to volatile Z, no synchronized with relation because thread A doesn't read anything from Z. And also synchronize, we have two different monitors, right? Y on A and V on B, so no synchronized with relation. How can we order them? From the perspective of thread B, well, if you're lucky enough and write to volatile X executed earlier, then thread B will execute operation 1, write to volatile operation 2, read the volatile, and then we have synchronized with relations, which means that any operation executed before, even if it's not synchronized, should be properly visible. The results of that operation should be visible for our thread B. So operations 1 and 2 results, we have access to them. And then operation 3 is synchronized V operation 4. Unfortunately, there's nothing about operation 3, 4, and 5 from thread A, because we don't have any other synchronized with relations. So that's the main game. So you have to find your synchronized with relations and try to order your code in some way. And then you can understand which writes will be visible from the perspective of the second thread. If we are less lucky, then write volatile is not executed before read to volatile, and in general there will be no synchronized with relations. Well, there will be, but between the initialization of your X and reading the volatile X. So, yeah. All right. And our thread-safe immutable objects, unfortunately, that's a completely different concept, which means that there are two things which you have to do to create thread-safe immutable object. You have to put final on every field, it's quite simple. And then there is a freeze action, which will happen after constructor has finished. So in general, you can put anything you want into constructor. So you imagine that you have a final field with a hash map, just hash map, not synchronized hash map. You will populate the hash map in the constructor, and as soon as constructor is finished, everything will be visible for other threads. So you can just share the reference to that object, and the other threads can just access that hash map as long as you are not modifying it, right? All right. So I mentioned earlier, we need to have final on our fields, and there is freeze action on end of constructor. Let's try to test that. In that case, we don't have final, and we are creating static immutable AI, so we are sharing the reference between multiple threads. And one actor is just creating the immutable object, and second actor is just reading the value x, y, z. If everything is fine, we should have only 1, 2, 3. If we have any zeros, it means that second thread has access to not fully constructed object. Let's try to run it. Okay, that should be not here, but here. All right, that's exactly the same code. And all right, let's see. And of course, I have to recompile. All right, one more time. And 1, 2, 3. Yeah, so what's wrong? So we don't have final. We are sharing reference with not thread-safe immutable object, and we don't have any zeros. The problem here is that it's x86 architecture. It can reorder only store with lots, and it seems that compiler is not doing anything extra for reordering. But yeah, what will happen if we run somewhere else? Let's take the same code and run it on architecture which has weak memory model. So do you remember the weak memory model can reorder store with store, loads with loads, etc., right? More reorderings are possible. So if we go to something which has weak memory model, like Raspberry Pi, which has ARM v7 with 4 cores, it's a great platform for testing. And let's run the same test here. So I have a helper script. So when you want to execute it from command line, you have to compile your jar, create your jar, and then execute from command line. And in general, you're providing -t with a regex to your test, -v to have verbose output. And it's also useful here to provide JVM args empty, because if you don't provide it, the framework will detect, all right, I have this specific JDK, and I can add extra parameters, like disable compilation or disable inlining, etc., and we'll run more tests, and we don't want to have that here. All right. Let's run it. And now the results are a bit different, right? With number of zeros. So our object is not thread safe. How can we fix that? Well, pretty simple. All you have to do is to put final, which something like this. There's no sense to run it on x86 because we know it's fine. However, we can also run it here. Again, the same syntax, right? Just final immutable. And now, problem fixed. So what's the lessons from here? We should always code against specification, never implementation. Because even if your code is working currently on your specific hardware, it doesn't mean that the production will have the same hardware. It doesn't mean that in 6 months, the new release of JDK will introduce some other optimization somewhere in compiler and start reordering. So to create thread-safe immutable objects, put final on every field, and then remember about the freeze action on the end of constructor. All right, so that was demo 3. And another test. This time it's called escape, and the name can tell you something about it. So what we are doing here, we are creating static in supplier Java functional interfaces, right? If you just provide the int, it's volatile. Then our escape class has one final field, so it should be thread safe. And inside the constructor, we are creating our supplier and also writing 1 to x. So once again, one actor is creating the class, and second actor is just trying to get the value from getX or from our supplier. Anyone want to guess what will happen here? So of course, once again, if everything is fine, we shouldn't have any zeros. If we have zeros, that means that we are accessing not fully constructed object. Oops. And that was escape, of course. All right. Well, now we have zeros. So as you can see, something is wrong. Now let me show you again the results. So 0, 1 is still possible. 0, 1 means that this value seems has escaped our this. So the idea here is that constructors are not ordinary methods. There's this freeze action on the end of constructor. So if you allow to escape this during construction, then you don't have thread-safe object. And that's what we are currently doing here, because we are exposing this on static reference, and other threads can access it before the freeze action has happened. So don't put your this on static references, don't create inner classes, which is quite similar to our in supplier. Don't create threads inside your constructor and put this into those threads, because they will not be properly visible. All right. Now I think it's time for Volatile. So we already know that writing to Volatile and reading the Volatile will create our synchronized with relations, which will be part of happens before order. So we can reason something about that, and we can have a great idea to optimize our code. So we don't need multiple volatiles, right? We can just have one volatile, because we already know that we will create happens before order, and all other writes should be visible. So this is another test, and this time our main optimization here is to remove one volatile. Of course, that's a stupid idea, but so what we have here is just writing 1 to y, writing 1 to x, and then one actor will write 2 and 3 to y and x, and second actor is just trying to read those values and multiply them. What kind of results can we get? Well, if actor 2 is executed first, we have just 1, which is fine. If actor 1 is executed as first, then we have 2 and 3, which is 6, which is also fine. If actor 1 is executed, and then in the meantime actor 2 is executed, so we will just write 2 to y. We will not have enough time to write 3 to x. Then we can have just 2, because 1 multiplied by 2 is 2. What's not possible here, if everything is fine, is to get 3. Because if you have 3, it means that actor 1 was executed first, which means that y is already 2, x is already 3, and the outcome is that I just have only 3, so what happened with y? All right, let's try to run it, because that will be more fun. So once again, 1, 2, and 3, 1, 2, and 6 are acceptable, 3 is forbidden, and it's our test. Oh, come on. Oh no, we have 3s. Something is wrong with our code. So our optimization is horrible, right? It doesn't work. Any idea? Any suggestions? Reordered? Which one? The actor 1, or? We can reorder actor 1, but we have to remember that the synchronized with relations which we want to use is between writing to x and then reading the x. So if we put writing to x before, then y is after our synchronized with relations, and it has nothing to do with it. It's like other operation. So that's close, but any other ideas? Yes. So the Java language specification will tell you that expressions are executed from left to right. So y is read first, and then we are reading x. Of course, it will also tell you that we shouldn't depend on that order, because it's a very bad idea. But in that case, the only thing which we have to do is just to switch x and y. So if we do that, so now we are writing 2 to y. There is no synchronized with relation, but that's one thread. Then writing 3 to our x, which is volatile. And then we'll have synchronized with relations with reading the x first, and then we can read y because the operation is already visible in our second thread. Let's try to run it now. Oops. And yes, problem solved. No more 3. So what's the lesson from here? Well, we should use higher level abstraction. If you don't have to go to volatile, don't go there, because even if you know what you are doing, it doesn't mean that other person who will modify your code will have the same understanding of that problem. So using high-level abstractions would help you to prevent those kind of issues. Or you can just put Volatile in another case, but you can also use some elements from concurrency package or something like that. All right, let's go back to our slides. So what's the future for Java memory model? We have quite old Java enhancement proposal. I think it's like 5 years old or something like that. It's still not planned for new releases of Java. But the problem which we have is that we need some extra formalization, which means that there are some scientific papers which are showing that there are some examples which shouldn't be there. So there are some flaws in our JMM. They can be improved. JVM coverage. Java is not the only language on JVM, right? So we have Scala, Clojure, etc. And they are using the same assumptions which we have in JLS. So probably they should be extracted. Some extended scope, like atomic weak compare and set. I'm not sure if anyone of you have used that before. Well, it's the same as compare and set in general, but it can fail from time to time. And as far as I know, implementation is the same. But there are other things like Java 9 var handlers, where you have specific access to our memory barriers, which would be nice for C11 and C++11 because C has now their own memory model, which is based on Java. We are not fully compatible with them. They have much lower access, which is probably not too good. And then we need some implementation guidelines for JVM implementers, which assembler instructions should be used on which architecture, etc. Testing support, JCStress is the candidate. It's already used on the new releases and new features. And some tool support and static analysis to be able to detect those kind of issues. All right, let's recap. So never ignore concurrency issue. They are real, they can hit your production and be very difficult to reproduce them. Use highest level abstractions as you can. Check frameworks for requirements about happens before order. Every mature framework will have something about happens before order to help you to understand which rights are visible. Code against specification, not implementation. Do you remember our Raspberry Pi example? Always code against specification. And if you want to create fully Threadsafe object, use final on immutable classes and then wait for the freeze action inside constructor, so don't allow the escape this. That's basically all. Thank you very much. So if you have any questions, then so the question is if JCStress generates JUnit report, which you can use for integration testing. It generates some HTML output. I don't think it's the same as the one which is in XML for JUnit, but it's quite possible to do it, to convert that one. But yeah, I'm just not familiar with if it's there. And in general, it's heavily used on OpenJDK, but if you have your own implementation of some code, if it's just the basics, for example, if you are creating your own implementation of non-blocking, linked list, or something like that, then you can think about using that. But for more complex architecture, for more complex code, it can be quite difficult to get the outcome. Any other questions? Yes? So the question is, can I comment on accessing or getting the...
In your example,
yes.
All of these variables are going to be packed in
yes.
hash line.
Yes.
Which means that when they become shared and invalidated, then there's going to be some internal...
So the problem which is... so the question is, can I comment something on the false sharing of the data?
That's not false sharing, actually.
All right.
Well,
So I.
Not really the point. The point is that the cache line packing might actually contribute to some of the effects that we're seeing in the benchmarks.
Right. So.
Not simply compiler reordering.
So the question is, can I comment on the cache line packing, which can affect one of the results of those benchmark? Unfortunately, I will admit, I cannot. Sorry. But we can discuss that later. I will be very interested to find out if you have more information about this one.
More questions.
All right.
I'm just curious about some of the valid results you're getting are more results of how the cache lines are managed, more than how the code is reordered.
Yeah, I assume that's quite difficult and also like hardware dependent, I would guess. But yeah, unfortunately, I won't be able to answer that. Any other questions? All right, if there are no other questions, then thank you very much and enjoy the rest of DevOps.